Hello, everyone. Welcome to Pre-Lecture 8. This is the start of Chapter 12 for us, an introduction to kinetics. Okay, so in the field of chemistry, kinetics largely refers to how fast a reaction will proceed from its reactants to products. And by understanding how quick certain reactions are consumed or certain products are formed, we can tell other things about a reaction, such as what we will call the reaction mechanism. We'll go through what that looks like more. Also, elementary steps. And so those are things that are basically substeps within a reaction that deal with something being multiple steps. And so these are all things we'll talk about, but just a little preview of where we're headed. Okay. And then, of course, this being general chemistry, we want to define these processes using mathematical terms. And so you get these things called rate laws that we'll talk a little bit about in class on Thursday. And we can obtain those from experimental data. Okay. So to start off, let's just talk about the rate of a reaction for a moment. And so this can be defined as the amount of a reactant or product per unit of time. And so this is usually determined by measuring the time dependence of some property related to our material. So that could be, for example, color. Could measure color appearance or disappearance. If a gas is involved, you could also measure pressure. Okay. So here's an example where we're looking at the decomposition of hydrogen peroxide. So H2O2 forming 2 molecules of water and 1 molecule of oxygen. And if we were to express this in terms of a rate of reaction, we would have this negative here because we're looking at the rate of decomposition. And so as this reaction proceeds from reactants to products, we're going to be losing our hydrogen peroxide, thus the negative sign in our equation. And so it would be negative change in the concentration of reactant over some amount of time interval. And so we could express that in another way where, say, that our rate is of hydrogen peroxide decomposition is equal to the negative of our concentration at some second time point minus the concentration of hydrogen peroxide at the first time point divided by, of course, the time difference there, so T1 minus T2. And ultimately, it could be condensed to this simple mathematical expression where we replace each time point with just a delta. So the change in concentration over the change in time. And of course, our negative sign is also still present there. Okay. If we were to collect this data and put it into a table, you'll notice here that on the furthest left, we have a time measurement and then a concentration measurement, and then essentially the difference between those. So the zigzag here indicates the difference in our concentration. Then, of course, this is our difference in time. And so, oh, pardon me, as this reaction proceeds, we're able to calculate the rate of decomposition at different time intervals. Okay. And you'll notice that as our concentration of our hydrogen peroxide gets less and less as we go from time 0 to time 24, our rate of reaction decreases as well. Okay. And so there are different ways you can measure the rate of a reaction. We're going to be talking about these quite a bit in class on Tuesday, next Tuesday, but I will mention them now. So for example, you could calculate the average rate where you would just look at the whole time period from time 0 to 24 hours, and that would basically be just the rate from beginning to end. You could also determine an instantaneous rate. So that would be from your time 0 to your first data point. And you could also, of course, calculate, or pardon me, the instantaneous rate could be between any 2 data points. So it could be between 0 and 6, or be between 6 and 12, 12 and 18, any of those values. We could also calculate the initial rate, and that would be specifically the rate between 6 hours and time 0. Okay. If we were to plot this graphically, this is another way to represent this where we could have, again, our initial rate calculated by the change in hydrogen peroxide concentration, which is shown here on our y-axis, over the change in time shown on our x-axis. And then we could do the same for an instantaneous rate where we're plotting two data points against each other. In this case, I guess 3 data points where times 6 hours, 12 hours, and 18 hours. And we're able to get the instantaneous rate there. Okay. All right. We're also able to express our rates of reaction in terms of the stoichiometry of a reaction. And so say we had this general reaction where we had some stoichiometric coefficient, this lowercase a, multiplied by some chemical uppercase a to form products in the stoichiometric amount, lowercase b, of chemical uppercase b. And so we could express that rate law in two ways. We could say that it is equal to negative 1 over A multiplied by the change in the concentration of A over the change in time, or the positive amount of B that is, of course, formed. And so these lowercase elements represent the stoichiometric coefficients. And then, of course, we're measuring changes in concentration over changes in time. To put this, oops, I showed the answer there for a second. So how would we express the rate of this reaction if it were basically taken this form? You could do that if you wanted to pause the video now. You could practice that, and I will go back and reveal the answer here now. So if we were looking at this reaction, our rate would be equal to negative 1/2 of our change in concentration of ammonia, this NH3, over a change in time. That would be equal to both the formation of our product, nitrogen N2, which would just be 1 over 1, as well as 1/3 of our concentration of H2 over time. And so if we were to express that graphically, it would look something like this, where as our reactant concentration is decreasing at a rate of 2, you could say, we see that our, if we were to compare the rate of formation of hydrogen, it would be 3 times the rate of our formation of N2, which of course ultimately goes back to our kinetics. Okay. All right, and so the other thing to consider with kinetics is how do chemical reactions actually happen? What has to physically occur? And so consider this general reaction where we have A plus another chemical BC, and the products that we form from this chemical reaction are AC and B. And so the steps that have to occur, first off, we have to have them actually physically collide, something that we maybe don't think about, but it of course has to be true that in order for a chemical reaction to occur, the two chemicals actually have to come in contact with each other. When that collision occurs, it must have a sufficient energy to break the bond between B and C in order for the bond between A and C to form. And then the reactant molecule A also must collide in the correct spatial orientation with B and C. So in order to form a bond with C, A is going to have to come in contact with C. And so, for example, say A runs into B, that might not be a correct spatial orientation, and that could be an unsuccessful reaction then. Okay, and so finally, if any of these three criteria are not met, a reaction will not occur. And so an example here might be where we have this molecule NOCl, and in order to form this molecule's nitric oxide, NO, and 1 mole of Cl2, what we just call chlorine, we have to have basically an effective orientation of the collision here, where we have to have our two chloride atoms collide in order to have an effective chemical reaction. So even if they have sufficient velocity to connect in these two other ways, the reaction would not occur there. Okay. We can, of course, define this mathematically using a term we call A, which is the frequency factor that describes how often this potentially successful collisions occur. And so this can be broken down into the orientation factor P and the frequency of collisions Z. And so to look a little bit more at those, the orientation factor represents the fraction of a collisions with an orientation that allows the reaction to occur. And so ideally this would be about 1, but the more complex your molecules are, the lower the p-value will be, resulting in less successful reactions. Okay? You'll also have to consider z, the frequency of the collisions, and this is a statistical value that will be determined essentially by our pressure, our volume, and our temperature of the reaction. Okay. And so finally, I want to talk about the activation energy of a reaction. And so this would be a barrier that prevents the reactants from simply being the products in the first place. And so in order for a reaction to occur where we go from our reactants to our products, they first must go through a transition state that has a higher energy value than our reactants. And so if our reaction is exothermic, we could say that our reactants start with this sort of potential energy, and they end up at products with this potential energy. Of course, our change in enthalpy would make this exothermic. But in order for that overall reaction to be exothermic, we have to have some sort of input to get over this hump in the transition state. Same would be true for endothermic reactions, except that our products will have essentially more potential energy than our reactants. Okay. Another thing that's true in this case is that the higher the energy of our activation barrier, the slower our reaction will be. And the position at the top of the activation barrier is called the transition state. This is the actual point where bonds are formed or broken, pardon me. And one thing about the transition state, this is something that must be hypothesized, can never actually be isolated. Okay. Some other things that may affect the rate of a reaction, it could be the physical states of the reactant. So if something is a solid, how much surface area it has might affect the rate of a reaction. You'd also want to consider the temperature and the concentration of things, and also the presence of a catalyst. And I will have more to talk about with catalysts in the future, so just wanted to introduce that concept before we get into it in a future class. Right, that's all for me today. I hope that that was something where you could effectively learn. If you have any questions, of course, write them down. Feel free to email me before class. Otherwise, feel free to ask them in class. All right, take care.